No, you can brief bit of relief. Actually, this is a companion talk to a talk that I gave this morning at Tableau, but I think that there is literally zero overlap between the two audiences, if I'm not mistaken, so I don't feel bad about repeating myself. Maybe if there is just one or two people, you can suffer. And this talk, the code actually, the technical work, formalizing the content of Tableau paper and doing some further experiments was done by my former student, master student at Erlangen, Maxwell Elliger, who is in here, before I moved to Italy. I hope that he's with us. Does this work?
Is it turned on?
Yeah,
or maybe it's not on.
Right now.
Yeah, let's see. Yes, it does. So we wanted to focus on a certain technical point in the formalization, in particular, whether we need to use certain decidable notion of state, whether a particular notion of state that we're using should be something going into bool, or something like a symbol, or rather completely arbitrary prop RT. But from the feedback that we got from the program committee and from the reviews, it seems that it might make sense to focus a bit on this mysterious inquisitive logic. So most of the talk will be spent introducing this system, and only towards the end or a bit later I will mention the specific technical problem that we found mildly intriguing and so, okay, this first line is slightly misleading. So inquisitive first order logic can be seen as an extension of classical logic, which puts declarative and interrogative statements on the same footing. That would be a better way. So here is a bunch of simple examples. You can find different examples in the abstract actually. So here we're going a bit in the direction of we consider setup whether we talking about, I don't know, potential murder or some other crime, and typical declarative statement, ordinary declarative statement that you can formulate in first order logic or even much less. Some description logic would be that Luisa is guilty. But then there are questions of dependencies, for example, between what we whether what we know already can settle some other issue, for example, whether our knowledge that Luisa was there would allow us to settle one way or another, it doesn't matter which one, but settle the question of Luisa's guilt, or whether if we are able to settle one way or another, but settle somehow the question whether Luisa was there, it would allow us to settle whether Luisa is guilty or not, or whether we can already establish that regardless of a scenario, that a specific scenario that took place, there is one person that we can say undisputably would be guilty in all those possible scenarios. So this means that the setup that we led to is when formulas are supported by sets of possible words, which and those possible words are ordinary first order honest to God relational models. So just to come back to our simple example, of course, we can play around with more mathematical examples with infinite collections and natural numbers, but let's stick to something unitary for the very beginning. So Luisa could be guilty or not, and she could have been there or not. So coming back to the statements or dependencies that we had on the previous slide, as I said, now we're not thinking just in terms of single individual first order model, but collections thereof, settling some issue or not. So for example, if in the word, meaning first order model number one, Luisa is guilty and was there, but in the word, but in the model number two, Luisa was there but is not guilty, then it means that even looking at this particular collection of two different models tells us that Luisa being there does not allow to settle the question of Luisa's guilt one way or another. Or if you just focus on the first and the third model, which answer differently the question whether Luisa was there and wasn't there, means that knowing that not knowing whether, but knowing that, so here we have no question mark, Louisa was there, does not tell us whether or not Louisa was guilty, this kind of stuff. So this is basically the intuition. And this means that when we're dealing with syntax, following standard references like books by Viano Ciardelli, we have syntax which is pretty much first order syntax, but with some bells and whistles. In particular, for example, when we're talking about individual terms, we can indicate whether a function symbol is rigid or not. Or individual constant is rigid or not, meaning that it would have the same, we insist that it would have the same denotation regardless of the specific model that we are looking at. So this is how our collection of terms looks at. Nothing funny happens when it comes to terms. But when you look at collection of allowed formulas, there is some funny business happening. So apart from standard Boolean setup. So of course we can also consider standard Boolean disjunction being just the De Morgan dual of conjunction. We have also this new kind of disjunction, inquisitive disjunction. And apart from standard existential quantifier, which is just the De Morgan dual or universal quantifier, we have another kind of funny looking quantifier, this double thingy, which is called inquisitive quantifier. But another way of looking at what this whole inquisitive stuff is that this is a weird super intuitionistic logic, which does not have very basic property of being closed under suitably defined uniform substitutions. Whether we have something that is known in constructive logic, well, maybe Topos theorists call it a bit differently, constant domain axiom. So we're always talking about the same domain on individuals, but possibly differing interpretation of individual predicates. And then, actually, this would be, as we are going to see, hopefully, if this slide survives my last slide, this would really behave like an intuitionistic implication. And this inquisitive disjunction is just honest to God Kripke-style intuitionistic disjunction in this setting. And this is just interpreted the way existential quantification would be interpreted in intuitionistic Kripke models. Because when it is sitting with in this constrained domain-like setting, there is no funny business happening with universal quantifier. And these two perspectives at inquisitive logic as an extension of classical logic and weird super intuitionistic logic not closed under central rules can be, of course, put together if you think of negative translation, especially Gödel-Gensen. So things maybe syntactic sugar or not for other. So, of course, in Rock, there are various ways of dealing with every setup, sorry, that has, what have I done? Can I return to full screen? Or just, maybe it's here? No. There are various ways of reasoning about syntax with binders and freshness and what have you, but probably the most standard by now is what Catherine Stark will give, even invited talk in a few days, the auto-substring, and of course, this is what Max Olle went for. It inspired him so much that he started to write even pen and paper in De Bruijn-like notation. So you see that sometimes that there are no variables after our quantifiers. And we insist on decidable. So in as much as things like predicates and function symbols are concerned, we can insist on decidable equality, and we implement arithmetics with arity types, arguments for argument functions. And then our syntax is parametric in this notion of signature. And then there is just a tiny bit, well, it will not impress you, I'm afraid, but just a tiny bit of fun that one has with notion of syntactic equality precisely because of dependent types. So the solution that Max Olle chose was to define setoid equality for terms and formulas here. Right, so this is nevertheless for those who are working with autosubs reasonably standard fair, I would guess. And then our notion of semantics, which is where somewhat more interesting stuff hopefully may live. So pen and paper, that's how we define it, formalizing some of the verbal definitions that I gave at the beginning of the talk. So our notion of a model has a fixed, as usual in this constraint domain setting, fixed collection of individuals. Those words are really just indices ranging over first-order models in question. Yeah, in case of those rigid function symbols, we insist that the interpretation stays fixed. And then, as I said, a subset, and of course here we have notion of a subset, is called an information state. And the question is whether then states should be, from Cox's point of view, just Boolean predicates of type where to bool, so something desirable by definition, or rather arbitrary function of type where to prop, which might be of interest, of course, when you consider infinitely many possible scenarios, infinitely many words. So semantics, but I didn't tell you something even more basic about semantics, namely, well, for terms, it's what you would expect. Again, this auto-subs, like De Bruijn way of writing things, sometimes makes for a bit more compact notation, even pen and paper, assuming that one can read it. And then for first-order formulas, one can say that the notation of a predicate at a state, this collection of individual models, we interpret it as just intersection of the notations of atoms, of relational atoms in individual models that the state consists of. And as you see, the clause for implication is really this intuitionistic implication where you really treat inverse inclusion on states as the intuitionistic partial question. And then, well, exactly what you would expect in that setting, in that particular type of intuitionistic Kripke semantics. And again, all I really like to play around with writing those definitions in this De Bruijn and auto-subs style. So we have various properties, standard properties, which you would expect in this intuitionistic setting, like persistence. Bigger in the sense of inclusion means less informational content. Then the formulas are persistent. Empty state is the absurd state. And then there is this notion of locality. So when you restrict your model to the subsets of the state that you are right now, you're not changing the value. And again, I'm not sure if this was the most economic solution or not, but in the end, the design choice that was made, that the definition of subtypes, so therefore the collection of individual models was chosen to be setoid. And then inquisitive first-order logic is logic of is the logic in this first-order syntax of all types of models of this kind. There is a natural reduction system by Ciarelli and Griletti, which is sound but not yet proven to be complete. And now for the bounded variant. So bounded variant happens when you insist that you have no more than finitely many scenarios, no more than finitely many alternatives, no more than finitely many models that settle things one way or another. Notice that it does not mean that we insist on finitely many individuals. Individuals can be natural numbers or whatever you want. And there are further restriction where you insist not just on being bounded, but n-bounded. So you insist that there are at most n such models. And those logics are much better when it comes, those restrictions give automatically things like, well, automatically, both for Ciarelli and Griletti and for us it requires some work, but one can get, if you fix n-bounded for a specific n, you can get complete, we know that we can get complete axiomatization one way or another. So Ciarelli and Griletti were extending the natural reduction system with something called cardinality formulas, but they were extremely heavily signature dependent. And the way they were designed, that would break down everything that one normally expect from anything looking reasonably like a natural deduction system with some computational interpretation. But there is also something else from our point of view. So this is stuff that I went into a bit deeper in this Tableau presentation, but from the point of view, the little technical issue that I want to discuss here, formalization contain, natural reduction system contain those specific rules governing the behavior of inquisitive disjunction and existential, and this inquisitive existential quantification, so-called split rules, which by itself look natural or innocent enough. The question is, what happens when you try to follow the proof of soundness that you give? Of course, that they give. Of course, it doesn't mean that this is the only way of proving soundness. Maybe one needs to experiment, but at least when one's slavishly to follow what is it in the paper, then the definition, the proof at some point uses such definition of a state for a classical formula and for a model M. This, as long as your signature contains not just unary relation symbols, means that the very notion of state being used here cannot be decidable. So it will be very hard to square this approach, or at least formalization or directly of the soundness proof that they are giving, with the use of Boolean predicates. So this is not what we did, by the way, because one of the flaws apparent in the way I wrote this abstract was that I suggested that we suggested that we tried both approaches. We didn't try this one too far, because this is precisely what discourages in going in that direction. And one of future ideas would be to try to experiment to put, like, having a more involved notion of state, where you have a flag, more dependent notion of state, where you can go one way or another and see what things are common and what not. But so far, this thing was not formalized in Cog at all. What we were formalizing in Cog was the sequencing calculus that I was presenting this morning, at Tableau, actually, even this very morning, which moreover provides in a kind of natural way sufficient characterization. We don't know yet if necessary, but at least sufficient characterization of schematic validity, also yes, soundness and completeness proof. We prove pen and paper, we didn't finish formalizing CAD elimination in Roc. We prove CAD admissibility. So in his experiments, Maxwell just hardwired CAD elimination in the system, but of course this is suboptimal. We hope to have funds and time and resources to do things properly in future. And this is just a label sequence system when labels are just finite sets of natural number, which are then interpreted simply by sending natural numbers to first order models. And in the setup that is in the paper or pen and paper development, we restrict to purely rational signatures, no function symbols, no complex terms, no discussion of rigidity. And Maxwell slightly adapted our calculus to cover non-trivial rigid terms, and this is already in the formalization. So this is an example of how those rules look like. And again, you see that when you're writing things in this auto subs, like the Bruin notation, one does not need to write explicitly eigenvalue condition, dagger. Here you assume something to be fresh, but it's there, staring in your face. Assuming again that one can parse this notation. So yeah, okay, this is the point that I already mentioned about CAD elimination. And here is what was supposed to be the clue for this, the key point for this short presentation. So labels are implemented by Alice in a suitable way, and proof of soundness for this set of rules that I sketched in the previous slide, not just allows, but naturally seems to require a decidable notion of state in the inductive way. So that was, at least so far, it was rather instructive for us that different design choices may be called for depending on the setups, closely related setups for very similar formalism, and it also indicates that one sometimes should think of, in order not to get into too much mess before starting implementing. As I said, of course, this is still, I mean, there are lots of specific challenges and questions in the abstract, but I would say that all of them boil down to one single point, that we should develop this further, and in particular, indeed, to be able to handle this natural reduction and sequence system in uniform settings. So, for example, show how on earth one can derive those weird signature-dependent cardinality axioms of charter regularity in our label sequence system. Of course, not only formalize CAD elimination, but also extending to cover the Maxwell proposed rules for setup with non-trivial, rigid and non-rigid terms, and so on and so on. The Tableau paper lists more and more challenges. Like, for example, given that this is a labeled sequence system, which does have CAD elimination, we believe independent paper proof, but if it's not formalized in COG, can we claim that we prove something? Can we derive somehow, as is usual in the non-label setup, correct interpolation result? Can we develop some kind of computational interpretation? Johannes Marti, for example, had some ideas how to interpret Gensen style system for inquisitive logic. So Lots of challenges, but of course, what I'm most interested in, I unfortunately also have to listen to another presentation in 10 or 15 minutes, but maybe now, maybe later on or during the next days, if anybody has some comments or feedback on how we're doing things, whether this is of any interest, whether something is promising, whether something is misguided, I would really love to hear that. So far, that's all I have on offer.